pleasure to be with you today, and hopefully we can explain this incredibly simple technology in a way that you can relate it to your constituency and to folks who may you may come across. Before we go too far, Jim and I really need to thank you folks for all the work you've done over the years in helping us to develop passive treatment technologies throughout the Commonwealth. There have been over 300 publicly funded passive systems built that have improved hundreds of miles of stream. But on particular note, we need to recognize the Good Samaritan Act, Growing Greener, the Act 13 funding, because that's how these systems get built. We are still left with over 5,000 miles of acid mine drainage impacted streams that can benefit from passive treatment systems or active treatment systems, as the case may be, that need to be addressed and get us to the goal that we all share of having clean water in the Commonwealth. As was mentioned in the introduction, some years ago I did some mapping on the extent of mine flooding in the Pittsburgh Coal Basin, and this map shows the Pittsburgh Coal Basin. This is the Ohio River here. Pittsburgh is up, actually right up here. Monongahela River is down in this area. Each of the circles that you see on the map represents a mine discharge, and these are primarily, although not exclusively, from underground mines. The areas that are shown in blue, these are mines that are flooded. The areas that are shown in this brownish color are active mines, or they were at the time, and the areas that are shown in gray are either unflooded or we don't know what their status is. What I need to draw your attention to are the circles. The diameter of the circle is proportional to the amount of the discharge. In other words, the bigger the discharge, the bigger the circle. So a circle that is this size represents 1,000 gallons a minute. If it's light blue in color, it's an alkaline discharge. If it's green in color, it's around neutral. And if it's red in color, that would be an acidic discharge, as measured by the alkalinity or acidity of the water. Waters that are circumneutral or net alkaline can have the potential to be treated passively. And as you look at this graph, at this map, you can see that the bulk of the waters that are shown are indeed light blue. So even though these may be huge discharges, they have the potential for passive treatment. Within the map, we have almost 5,000 square miles of mine land, of which almost 2,000 square miles are flooded. This represents 1.36 trillion gallons of water that is in storage in the underground mines. We're currently discharging about 27 billion gallons per year, and 63% of that does not go through treatment. This would be water that's coming from legacy sites, the legacy in this case being mines that closed prior to the Clean Water Act or the Surface Mining Control and Reclamation Act. Of this, almost 38% of the acidity is untreated, 40% of the iron is untreated, and almost 100% of the aluminum that is present is untreated. There's a reason for those variations in the numbers, and if you need more insight on that, I'd be happy to tell you why. but this isn't we aren't to the Trompe yet. Just an example of some discharges here. This is Coal Run. You can see the orange staining on the rocks. The orange represents iron, and this is a circumneutral pH. The Presto Saigon discharge, we're seeing white staining on the rocks, and this is representing aluminum that's coming out of the water. So, to the topic, what is a Trompe? It's a device that uses falling water to compress air. It has no moving parts, does not use any electricity, and it's completely passive. So how is this possible? Well, Trompe has a vertical pipe, and water falling down that vertical pipe entrains air bubbles. The velocity of the water carries those air bubbles down. So the velocity is going down faster than the air bubbles can go up. So the air bubbles are carried down. I'm going to flip back and forth between a couple of slides because it'll make it easier to understand. So here's our vertical pipe coming down. The air bubbles are carried down, and down here, the air bubbles separate and float to the top and are captured in these air chambers. The water without the air in it travels along the bottom and moves over here to the discharge. So as you can see, it's completely a flow-through device with the only catch being you have to entrain the air particles. And that is accomplished by the air injection head here, which creates a bit of a Venturi effect, which allows the air to be sucked in and entrained in the water flow. So as we saw in the diagram, the air follows down the pipe to the separation chamber, separated by gravity. The air is collected and the water is then discharged. The Trompe itself is not a treatment. It is an air compressor, and it allows us to compress the air to a pressure that is sufficient for the needs that we're going to apply it to, which is going to be the aeration of a pond. The length of this pipe dictates the amount of air pressure that we're able to achieve. The longer the pipe, the greater the air pressure. Fortunately, for our purposes, we only need to have a pipe that is less than 13 feet long. We typically, or ideally, would do our aeration in 10 feet of water, and we have to have some additional pressure generated in order to operate the air diffusers. Trompes tend to operate in a bit of a narrow flow range as dictated by the diameter of that downpipe. So we need to know what the flow rate is at a particular site in order to be able to design the system to accommodate the range of flows that we're going to see. The next site that we're going to look at ranges from about 25 gallons a minute up to 150 gallons a minute. And at that site, it was necessary to have 3 vertical pipes in the system so that each one would handle up to 50 gallons a minute. And if we were just operating one, it could operate at 25, but not any lower than 25. The other thing that's important to note here is that we can generate 1 cubic foot per minute of air for every 25 gallons per minute of water. I apologize for the mixed units, but it's easy for us on the English system to understand how much air is being compressed. Okay, this is at the North Fork site. It has recently been installed under a grant from the Office of Surface Mining. to develop this technology. And this is the site that where I mentioned we have the flow range. So the lowest pipe, this one right here, it sees the water first, and it sees the first 50 gallons per minute. So it starts operating, and as the flow increases, then the next down leg starts operating, and then the third leg starts operating, so that we end up in total with 150 gallons a minute of flow being generated. We have also demonstrated at this site that it is possible to use the water over again. We have 3 Trompes that are in series. So this Trompe is here, we have another Trompe that is located right there, and the third Trompe is down here. So by running them in series, we are able to multiply the amount of air that we are generating from the same amount of water. So 3 Trompes, 3 times the air for the same flow rate. The Trompe is originally developed in the 1600s, 17th century, probably in Italy, but it was really picked up by the Spaniards and became an integral part of what is known as the Catalan forge. And they would have their vertical pipe, which would probably have been maybe a hollow tree, and they would cascade the water down, and it would be caught in this air box, and the air would then be directed into their forge instead of having a bellows. And you may have heard of Catalan steel in the past, but they're quite noted for their steel making many centuries ago. In fact, the Spaniards brought Trompe technology to the United States and built a couple of Catalan forges in California. Well, that technology was kind of lost for a time, and a fellow in Canada by the name of Charles Havelock Taylor rediscovered the principle when he saw water coming over a waterfall and entraining the air and creating blisters and bubbles in the ice that was on the surface of the water. And he connected the dots and started building these things, and he built massive Trompes. The biggest one ever built was at Ragged Chutes near Cobalt, Ontario. And as you can possibly see from the diagram, this vertical shaft, up at the top, that vertical shaft is 9 feet in diameter. It went down 345 feet. Now, obviously, they are using miners to build this, not excavators, right? The horizontal section where they separate the water from the air is 1,000 feet long. The return pipe is 22 feet in diameter and 298 feet long. They diverted the Montreal River into this thing. It generated over 5,000 horsepower. It was able to compress air to 128 psi. Remember, I told you the length of the return pipe dictates the amount of pressure you generate. So that's this length of return pipe was able to generate the 128 psi. It operated for over 70 years and was taken down only twice for maintenance. The compressed air from this Trompe was piped to the silver mines around Cobalt, Ontario, where they used it to run the rock drills, you know, pneumatic hammers. And, you know, as a side benefit, the miners got some ventilation. So, getting back to mine drainage, when do we have to have aeration in mine drainage? Well, we need aeration when ferrous iron is present. The orange stuff that you see is ferric iron. So we need to convert ferrous iron into ferric iron, and you do that by adding oxygen. You also have a need to add air, add oxygen when you have a low dissolved oxygen content. Typically, water comes out of some of these underground mines very close to 0 DO. I mean, 0.02 or very small numbers. The third time you would need to aerate is when you have a dissolved carbon dioxide in the water. And the effect of carbon dioxide is to lower the pH of the water, to make it more acidic, because it dissolves as carbonic acid. In the flooded underground mines, you have an environment where acid in the mine water can react with calcite that may be present either in the rock dust or in the rock surrounding. This raises the pH, but it also releases carbon dioxide, and that carbon dioxide can dissolve in the water, pushing the pH down a bit. So if we can remove remove the carbon dioxide from the water, we can raise the pH of the water, and that's raising the pH is part of the treatment that is necessary at a number of these passive mine drainage systems. So in this chart, the key thing to take away from it is that as the pH rises, the amount of time that it takes iron to oxidize diminishes from years to months to days. When you get up here in the vicinity of pH 7, it only takes minutes for that to happen. So instead of having to have long retention times for the reaction to occur, if we can get that pH up near 7, we can make that happen a lot faster. So we started doing aeration tests. This is the Curly site. It's the first site that we put a Trompe into, and all this is we have an aquarium aerator, air compressor, with a little sparging stone inside a column of the raw mine water. We grab it as soon as it comes out of the mine. And as you can see, just by blowing air through it, we're able to raise the pH from 6 up to 8. This means that by getting air into the water, we're taking the carbon dioxide out, we're exhaling the carbon dioxide, and we're simultaneously putting oxygen into the water. This is another site that we've recently put a grant proposal together on Act 13, or Act 13 money. This is a very high volume discharge that has a very small physical area available for treatment. And one of the benefits of using the Trompe technology is that you're able to minimize the size, reduce the size of the treatment system necessary because you're able to speed this process up. And again, you can see here that we're going from a pH of about 6.2 to 7.3. And the next graph, what I want to show you from this graph is that technology is not limited to the bituminous coal areas. This is also applicable in the anthracite. The Old Forge discharge is a huge discharge coming into the Lackawanna River, and you can see that again over time we were able to raise the pH from 6.2 to 6.8. Now this is the Curly discharge, and this is the raw water that's coming into the system, and you can note that the water is crystal clear. That's because the iron is completely dissolved in the water and is very content to stay there until you start changing the aeration of the water. And down here at the bottom, this is air that is bubbling through the water. That air is being produced by one of the Trompes that we have built at this site. And we are beginning both the process of exhaling the CO2 and dissolving the oxygen into the water. I apologize for the chemistry, but very simply, if you have ferrous iron, add a quarter mole of oxygen, consume a hydrogen, you basically get your ferric iron and water. If you do the chemistry, you do the math, basically it means that if you add 1 milligram of dissolved oxygen, you can oxidize 7 milligrams of ferrous iron. And as we learned, it's a time-dependent reaction. So here at the Curly site, we saw where the raw water comes in, and we're looking at the dissolved oxygen content here. And it falls into a plunge pool, which takes it from essentially 0 to 1 milligram per liter. Right at this point, we have the Trompe aeration taking place, and immediately after the Trompe aeration, we've moved it from 1 milligram per liter to about 6.5 milligrams per liter. Now, if we add additional aeration there, and we did, but didn't measure it, you can obviously take the DO up to its normal saturation level, which is about 10 to 11 milligrams per liter, depending on temperature. At the same site, we can see that as it's flowing through the system, the pH of the system is also rising. We were able to raise the pH from about 6.3 to 6.6, so we were able to raise it 0.3 of a pH unit just flowing past the Trompe aeration. This is a picture of the Curly site from the opposite direction. You can see this is the raw water coming in, and this is the aeration taking place. The physical location of the bridge is right here, so we are measuring pH of the raw water, pH in the plunge pool, and pH right here at the bridge. So that's where where our controls on the system are. Now, you notice the color of the water. We're starting to get a greenish kind of color here, becoming a little bit opaque, and over here in the next pond, these flow this way and then back. We see the bright orange color that we normally associate with mine drainage. When this discharge was running without the air on, both ponds are crystal clear. We hadn't even started to oxidize the iron yet. And so we were having problems at the discharge into the treatment system because the iron wasn't coming out as it needed to. I'm going to draw your attention now to the size, the amount of air bubbles that you're seeing there. This flow rate is about 60 gallons per minute and is coming from a single trompe. The next photo is from the North Fork site, and this is coming from 3 trompes in series at 125 gallons a minute. And you can see the significant increase in the amount of air that's being bubbled through the system. The amount of air that you can transfer is a function of a number of factors, one of which is the size of the air bubble. If you have a big air bubble, you have a fixed surface area. But if you take that big air bubble and break it down to a bunch of little tiny bubbles, you have ever so much more surface area. And it's that surface area that controls the transfer of either the carbon dioxide or the oxygen between the gas and the water phase. So it's important to have a fine bubble aeration. We accomplish that aeration using a disc aerator. These discs have very tiny slits in them, and the slits allow air to bubble through and make very fine bubbles as they do so. These discs are off-the-shelf technology, and they are used in sewage treatment systems because, in a sewage treatment system you have to aerate on the anaerobic step. You need to aerate to keep the bacteria moving and eating up the discharge. Unfortunately, in a situation where you're oxidizing iron, the iron can start to deposit on the disc, which is represented here by the ugly one. These discs can be easily cleaned using hydrochloric acid, and you can either remove them from the bottom of the pond or actually treat them while they're still in the pond. We've developed technology or methods for treating them in either scenario. The other thing is depth. If you double the depth, you double the oxygen transfer for the same amount of air. So we try to work at 10 feet. Going deeper than that becomes impractical to dig the hole that's necessary for the trompe. Shallower than that, and you're not getting enough bang for your buck. Just a couple of graphs of what we were able to accomplish at the Curly site. This percent iron oxidized started off with 0. The orange line represents no aeration. This is what the system was doing prior to building the trompe. The middle line, we were at low, the trompe was running, but at low flow, so we weren't getting the maximum amount of air coming out of the system. And the green line is fully aerated, everything working properly. And you can see that by the graph that we're able to more rapidly oxidize the iron as it moves through the system. Some more results, and the amount of iron settled. The colors remain the same, red being not aerated, the bluish color partial aeration, and the green color the trompe operating correctly. Basically, if we're able to oxidize it, we're able to settle it. So what do these things cost? Well, it's a function of size. We typically build these out of PVC pipe, and for the smaller flows, you can actually buy the pipe that you need at Lowe's or Home Depot. As you get into the larger flow rates, you have to go to the specialty plumbing houses that have the 10, 12, 14, 16-inch diameter pipes that are needed. And the costs for those size fittings are remarkably different from what you're used to seeing at Lowe's and Home Depot. So for a flow rate of 20 to 100 gallons a minute, you're looking at about $12,000 to do a turnkey operation, buy the stuff, get it to the site, bring the excavator in, dig the hole, assemble it, and plumb it into the site plumbing. As you get into bigger flow rates, you're looking at additional amounts of money needed to build the system. I'm going to switch gears now a little bit and talk about a semi-active lime dosing system. And this is at the Manor site, and it is a pebble quicklime system that uses a water wheel to distribute the quicklime. The problem with some of these water wheels is this sludge accumulation. This is undissolved lime. This is lime that is put in the system but never was utilized because it just didn't dissolve. Tim had a great idea, and that was to use by the way, this is what pebble quicklime looks like when it comes into the facility, and you can see there are large lumps in there and there are fines. It's all mixed up together. Tim came up with a mix well concept in which mine water flows down into the bottom of this vertical pipe, and the pebble quicklime is added along the outside. And this creates a bunch of turbulence down in the bottom. The pebble quicklime falls to the bottom and gets rattled around. And we call this an autogenous grinder, a self-grinder. And as a result, this is able to degrade the pebble quicklime into very much smaller particles. This is a picture of the mix well in action. The lime is being fed in here and dropping down, and the raw water is coming down the center pipe, and the overflow pipe going this way takes the mixture downstream. And as you can see from this picture here, those lime particles have been significantly degraded to a much smaller size. But we still want to get the value from this lime as well. And so I came up with a concept of the A mixer. And in this concept, we are using air from a trompe, which is being fed down the center of this pipe. And this is a vertical pipe that is suspended off the floor and below the surface. Air from the trompe is allowed to bubble down the bottom of the pipe, lowering the density of the water in the pipe. The denser water on the outside forces its way in, and you generate a circulation. This circulation allows those particles to remain suspended while they continue to dissolve. And this gives you a view of what that looks like in action, where you have the air causing this bubbling and this upwelling of the water in the center, and continued mixing of the water in the tank. Just for jollies, you may notice that this water is green. Iron comes in two colors. Ferrous is green and ferric is orange. And so we have a lot of ferrous iron, and as we bubble air through it, we are also starting to oxidize the iron at the same time that we are continuing the mixing of the pebble quicklime. And this is a picture of the pebble quicklime after it's gone through the mix well and the A mixer. These are graphs of particle size distribution. Basically, we put the material through sieves, and the raw material, 60% of it stayed on a 10-mesh sieve, and very little of it was fine. By the time it came out of the mix well, we had 80%, 100% went through the 10-mesh sieve, and 80% was retained on the 60-mesh sieve. And by the time it left the A mixer, these are 2 different days here when we did the test. We're between 40 and 55% retained on the 60, and again about 50% retained on the 80. So we're continuing to utilize the lime. But what this translates into is a 40% reduction in the cost of lime at this treatment site, which is being managed under
Shannon DMO.
The Shannon DMO is basically paying for this. So these are Commonwealth dollars that are being saved. Okay, so what other technologies, what other applications might there be for Trompe technology? Obviously, we have mine drainage treatment, and that can be either active or passive. There are a number of active sites where mechanical aerators are used, and people are spending money on electricity in order to aerate the water, where they have a flow that could drive an air compressor that would save them the cost of the electricity and the cost of the maintenance on their mechanical system. Clearly, sewage treatment is a possibility. If you have a water level difference, and by the way, I guess I never mentioned it, we need 4 feet of water level difference in order to drive one stage of a Trompe. If you have that discharge on your sewage treatment plant, you could run that through a Trompe and then take your air back to the aerobic bacteria step and either replace or reduce the amount of mechanical aeration that you have to use. You could use it in aquaculture. Fish need to breathe, right? And if you have a lot of fish penned up in a small area, I expect they would grow faster if the DO levels were high. Lake aeration, some people use it for algae control, and obviously you can use it for chemical mixing. And I was thinking after I did this, there are a number of streams on the impaired list for the Commonwealth that are impaired because of low dissolved oxygen. So the payoff there may not be great because low DO sections of stream typically don't have a lot of gradient. They're flat, and of course we need 4 feet ahead. But there may be we may be able to bring in side streams, or there are lots of possibilities to consider. So I'd like to say, acknowledge Tim and Biomost because they stepped up on Curly, and they saw the benefit of the technology early on. Tim, who will happily do anything in January. Brian Page, who the man is amazing. He'll walk right into a yucky sludge-filled pond in January. And also need to acknowledge Cody. So at this point, happy to take any questions you may have.